Okay, good morning, all of you. We'll see today classifications of optimization methods. We can see here first before going to that, there is a different methods are there. You can observe in this table they have given different kinds of conventional as well as the modern techniques also. Earlier we can use the calculus method and calculus of variations, nonlinear programming, geometric programming, quadratic programming, linear programming, dynamic programming. Like this, we have many conventional methods available to calculate or to find the control parameters. Now, whereas if we see modern techniques, in this we are going to observe the modern techniques only, rest of the units. And this is all about the introduction. We will see what are the basic things. And now we can observe these are the modern technique, genetic algorithm. This is our second unit. And simulated annealing, ant colony optimization, PSO algorithm. This is the third unit, and then neural network, fuzzy optimization. Like that, we may have Cook search algorithm or harmony search algorithm, or ant colony algorithm, honeybees algorithm, or like that. We may have many different kinds of algorithm. This is the methods of optimization. Now, why we are going for optimization? We can see some applications wherever any engineering field, for that matter, not only electrical, it is all related to. We could go for civil or mechanical or chemical, like that. We can use the different kind of applications using this optimization algorithm. We can able to design that. So in that you can see aircraft and aerospace structures for minimum weights, and then finding the optimal trajectories of space vehicles, civil engineering structures, such as frames, foundations, bridges, towers, all these things we can able to design like less weightage on the bridge where you need to use the pillars and all. So like that, we have design parameters, many design parameters involved in that, and the minimum weight design structure and design of water resources for maximum benefit, optimal plastic design structure, linkage of cans, gears, and machine tools. And this also an application. Not very few I shown you here, but thousands of applications we can see in any field. We can even our case, electrical case also, machine design, optimal parameters. So suppose objective is maybe minimization of the size of the machine with the same capacity. We can observe in the olden days machines, we have a lot of size, size of the machine will be very high. With the same capacity now, the size is very portable. Like mobile phones, initial 90s and all, we can observe mobile size and weight will be very bigger. But now it is very weightless and size is also compact size and all. Machine matching conditions in a metal cutting process, minimizing the cost and all. Design of material handling equipment, design of pumps, and design of turbines, and optimum design of electrical machinery, electrical networks, shortest route, and optimal production planning. Like that, if you see, keep on, many more applications are there using this optimization algorithm. So that is the reason In nowadays, all the things are very popular. The heuristic algorithm, we can say hybrid algorithms, all these things are popular nowadays. And you can see some of the journal papers also. The NASA developed easy warning system for detection of coastal disturbances. Or Ashok Leyland also they used ride comfort with Simscape model, cap suspension. Like that, I can, if you Google it, many more applications are available are using in our real world problems. And now optimization problem means before going to numerical, object function, now we can able to understand optimization problem, traveling salesman problem. Let us do that. There is some cities A, then B, C, D, E, like this. There is a five cities are there. What this man we can say is optimal salesperson want to find the minimum cost route. We can go many ways. You can see, suppose for example, if I draw one rough route, A, and it will go to E and then C. Then if we go to D, then what? How to meet this guy? I mean city B. So he has to go like this, or it has to be like this. So like that, our alternate many options are there. Now, what we need to identify from that options, we can see that which is the minimum, cost route. Then to avoid the total kilometers maximization, here is a minimization problem by this case. Instead of going A to E or something, you can able to go some other way also based on the distance. You will start with A and it will go to B, C, and then D, and you may come to E. So this way also one direction. So that means based on our distances, where to go first, and then like that we can able to observed things. So once if we are able to identify the shortest path, that is only their optimization problem. Each city is visited exactly only once, cannot go twice and all, so that it will be minimized. That is one problem. Another thing you can see, map coloring. Four set of colors identified, and we need to color the given map. For that, no pair of neighbors countries can have the same color. So what we'll do, if I mark one color for this, the next adjacent country should not be same color. We need to change that color using this blue, white, yellow, green colors. That is also one optimally we have to identify the countries with different colors you need to quote. And another problem, you can see that knapsack problem, in that what is there in a bag, we need to fill that bag with these weights. So given set of items, each with weight and then values is given. Suppose you can see 2 kgs and $2, and 1 kg $1. Then another weight with weight and then cost is mentioned. What we need to determine number of each items to be included in the collection, so that the total weight is less than or equal to given limit. So what is the limit is a 15 kg only our limit is there. So now we need to select weight such a way that that's what we need to determine the items. So how many you need to include, but while we are including, this has to be satisfied. What is our satisfied? Less than or equal to 15 kgs are related by or equal to 15 limits, and total value is as large as possible. So the weight should not increase beyond 15 kgs, but we can able to the insert the these things will be weight, what you call as cost must be more, so that we have to keep it in your bag. Which box should be chosen? So now to do that, we optimally what are the combinations of bags we have to use to fill within a 15 kgs of weight. That's one thing. Another one, there is some definitions are also called as some parameter names. You can remember a decision variable. This any optimization problem while we are forming, being with identifying the decision variables. What are the control variables we need to control to get our variation in the objective function to get their desired requirement subject to the constraints. Relate the objective function and then constraints, you can see, can be continuous and semi continuous or discrete fashion. You can see there is a continuous one, semi continuous or discrete fashion. All these things are available. Choose a paint color in a decision variables. Possible value of the decision variable, let us assume that these are the colors, can be bound or within a bound. So like that, we need to decide our decision variables. And similarly, there is objective function also is required to the function is maybe minimization function. We need to control the decision variables to get as a minimum function value. Suppose if any function is said to be as a minimum, this point we need to identify. Our maximization problem, you just multiply by minus sign, we can able to minimize that function. We can easily get as a optimization problem like that. So can be bounded or unbounded. Absence of objective function in the presence of constraints. You can see that any objective function subjected to the constraints also there. That's what after classification, it is all introduction only. Then we'll see some classifications. So after that, we'll move on to constraint problem and unconstrained problems as well. Now we can see the what are the constraints, how we can define it in our problem. Let's consider there is a two major constraint. One is inequality constraint, another one is a equality constraint. What is meaning of inequality constraint? Resource constraint, that means in general denoted by g of x is less than or equal to 0. Thus we call it as a inequality constraint. What is meaning x? That may be g of x is a one function. Let us assume that that function may be x1 plus x2 or greater than or equal to 10 or less than or equal to 10, whatever, that is a function. Now the while we are finding the parameter, or while we are minimizing the objective function, the objective function also consisting of x1 and x2, let us assume that. After optimizing that, the x1 and x2 values must be less than or equal to 0 or greater than or equal to 0 or equal to 0. Like that, we have to check the constraints. So if it is less than or equal to 0 or greater than or equal to 0, that we call it as inequality constraint. But if it is equal to 0, then we call it as a equality constraint. So that's what all these things is related to equality constraint. This we call it as a inequality constraint. For that, any objective problem or objective function consisting subjected to some constraint. Some cases both may be there, inequality constraint and equality constraint. Some may be only one constraint may be there. Some may not having any constraint, that is unconstrained problems, that also we'll see later point of time. What is meaning of feasible solution? Satisfies all the constraint. So suppose this thing also subjected to constraint, this also subjected to constraint. When the problem is said to be as a feasible or optimal problem, are these variables, whatever you are getting x1 value and x2 value, that x1 and x2 value has to satisfy this equation and also for this equation, and this equality constraint and both constraints must, both in the sense many number, it may be broadly can classify inequality and equality constraint. In that, if all the constraints are satisfied, then we can say that a feasible solution, that is will satisfy all the constraints. What is meaning of infeasible solution? It does not satisfy at least one constraint. So suppose even all constraints are satisfied except one, then I can say the problem is a infeasible solution. So when the solution is said to be as a feasible, all constraints must satisfied, and it is infeasible, or if any one of the constraint is not satisfied also, we can say it is a infeasible. Another one is a hard constraint and soft constraint. So they must be satisfied in order to accept a solution. And soft constraint means, suppose hard constraint indirectly, suppose x1 plus x2 is equal to 10, and then the x1 value and x2 value must be equal to 10. It should not allow any, what you call it, as a relaxation. But whereas soft constraint, I can say some tolerance, you can make it use that x1 plus x2 or less than or equal to epsilon or something. That kind is different. That is a soft constraint. So that's what allowed to relax to some extent to accept the solution. But let's assume that one example, generation must be equal to demand. Let assume that. Let neglect losses. In Indian power plant, generation is equal to demand. In general, exactly may not be reached that point. So then you can say that generation minus demand are less than or equal to some epsilon, or the maybe point not one or point not two or something. If you make it that, that we call it as a sub constraint, we can accept some extent. But whereas here in the hard constraint, it is a direct solution process. The generation must be equal to demand. Now, feasibility, as I mentioned, no feasible solution and infeasible solution. For that, I'm giving one small example to understand. Some function, you can take it any function, may not be like this or any some other, you want, you can take it as x1 plus x2 or something. That also you can consider 2x1 plus 5x2, anything. That is a one function, let us assume that. Now there is a function f of x is equal to something is mentioned, and subjected to constraint is given. What is the subjected to constraint? Pi x1 square plus x2 by 4, the must be what you call it as greater than or equal to 300. What is meaning g of x greater than or equal to 300, where g of x is nothing but a pi x1 square x2 by 4. Let, after optimizing, let you may have solution for that function x1 and x2 value. One case may get something like this. If x1 is 3, x2 is equal to 10, then substitute here. Then if it is satisfied, I mean that value is greater than 300, then it is a feasible solution. Otherwise, it is infeasible solution. Now you can see I substituted x1 is 3, x2 is equal to 10. Then our function I got f1 is equal to 7.05. Let it be. And what is g of x we got? 70.69. Then what they mentioned, g of x must be greater than or equal to 30. Even though whatever you calculated x1 and x2 minimization, but it is fails to meet the constraint. That's why this solution will not take it into account. That is the problem actually. Even though the cost may be minimum, like same, I will explain in terms of generation, thermal power plant, I want 10 megawatt, let us assume that. But our well, we are using two units. One unit I assigned 3 megawatt, another unit I assigned 7 megawatt. And you may get the cost of generation is equal to less. very less value. Let us assume that. But while you are assigning generator 1 is 3, generator 2 is 7, but whether we can able to assign or not, you have to check. What is that checking condition? The reason is the generator 1 capacity may be 5, what you call it as 5 megawatt. Generator 2 also 5 megawatt. But what you assign, generator 1 is 3, generator 2 is 7 megawatt is assigned, because that condition is failed. So subjected to constraint that maximum capacity of each unit may be 5, but you assigned second one is 7. That means I can say the value may be minimum, but subjected to constraint is fails. It is violate the constraint. That is the reason I can call it as a infeasible solution. Such kind of thing we cannot consider in account. So now, what is another solution? Let's consider x1 8, x2 is 6. Now you substitute this x1 and x2 in the function, you got something value that is equal to 16.34. And what you got, if same x1 and x2, if you put it into g of x, you got 301. Now g of x is greater than or equal to 300, then now we got it as 301 something, therefore it is a feasible solution. So this is the way we can able to understand whether the solution is feasible or not or infeasible. You need to identify the things. Then the bounded, this also we need to consider. Here the bounded means the function value as well as the variables also is going to be bounded. Like generators, as I said, generator 1, generator 2 values is known, but whether it is within the bound or not. Generator 1 is 3, generator 2 is 7 megawatt, but as per our, let assume that the problem of the generator 2 capacity is only 0 to 5 and 1 also 0 to 5, but your getting value is 0 to 7. You got it 7 megawatt, no, you assigned. That is the problem. We can say that whether it is within the boundary or not, we need to check. Now, one problem we can see, let it be as a what you call it as a function, minimum f something, and f value is given, x1, x2 value is also given. And this is one function, let us assume that in that, what is mentioned, x1, x2 boundary is also mentioned. Even though x1, this is one problem, let us assume that another case, they mentioned x1 boundaries, x2 boundaries. So whatever you are going to minimize this, x1 must be 0 to, 100 to 700. X2 is 50 to 100. Within this only we need to consider. So in that case, we can observe feasible region. What is feasible region? Let x1, x-axis is x1, y-axis is x2. Then I can say feasible region 100 to 700 x-axis. This is starting point, ending point, and x2 value 50 to 100, then this is 50, this is 100. So in between this region, I can say is a feasible region. Now we can observe this will be as a our feasible solution. Now whatever x1 and x2, while we are minimizing, that values must be within a limit, then only we can say it is a feasible solution. Otherwise, we cannot consider that solution into account. Other problem you can see. Constraint boundaries is given, x1 minus 3 x2 is 400. This is another constraint. Here they given x1 limit is given, x2 limit is given separately. And another case you can notice here, x1 minus 3 x2 greater than 400. Now, if we solve this, something x1 is 0, and then if we put here, you will get the x2 value. Now, x1, x2 is known now. Then we can see the region is going to be different. Instead of earlier region, now it is very only this region is within the boundaries. And similarly, the function also greater than or equal to 800. Then if I substitute x1 value, you got it, x2 value, you got it. But of course, x1 and x2 are within the boundary, but region is going to be changed. So like that, feasible region only we need to get the solution. This is the first topic in our syllabus, classification of optimization techniques. There is a different classification. I will keep on explaining different kinds and based on nature of that variable or different kinds. It is only the remembering concept only, nothing is there. The mathematical programming techniques also there. What are the mathematical programming techniques? I think some in the UG class there is optimization, the or optimization research or optimization techniques like that. From there, you may be studied simplex method and dynamic programming, all these things. Simplex algorithm and interior point algorithm, and then steepest descent method, Newton's method, quasi-network method, and these are all the cutting plans. So conventional methods that we call it as a mathematical programming techniques. So classification based on mathematical programming techniques, we can list out this. And other one, classification based on the meta-heuristic techniques. So this is what I mentioned yesterday's class also, natural inspired algorithms. In meta-heuristic technique, you can see genetic algorithm, this I mentioned second in it, then PSO third in it, and D fourth in it, and combining all these things with application is a fifth in it. That's what our syllabus is going to be. Like that, many thousands of lakhs of algorithms also there. But if you understand any one algorithm, and that will be suit for you to what you call it as understand other type of algorithms or hybrid algorithms, anything is possible if you can able to understand any one of the algorithms. So that's what our intention. And this is the other technique algorithms also we can see. There is a neatly mad simplex search and Fibonacci method and golden section method, like that. Other algorithms also we can cut. This is the one classification based on the mathematical programming and based on the meta-heuristic techniques. Now still I will cover some more after this problem formation. And this is the statement of an optimization problem. In optimization problem, always there is a function and then constraint. So this is our f of x is our objective function. In that, in x may consisting of different variable. Suppose f of x is equal to x1 square plus 2x2 something and minus 3x3, like that. If we may have, then what is this mechanism? We can able to write x1, x2 and x3. So this is the f of x is a vector. We need to find the variables x1, x2, x3 and so on xn. That variables might there is a equation objective function it consisting. Now while you are solving this f of x, now our intention to find what is x1 value, x2 value, x3 value, then only we'll get what is the f of x. And once if you know x1 and x2, x3 value, it has to be satisfied this condition also. G of x less than or equal to 0. G of x means something another combination of equation. Let it be x1 plus x2 is less than or equal to 20. Let us assume that. That is g of x. Now we are calculating x1, x2, x3. Put it here and check this condition is satisfied or not. Similarly, equality constant. Some cases they may say that something x1 plus x2 plus x3 must be equal to 200. Let us assume that. Then these variable, whatever you are finding above, that must be satisfied and this constraint. So this we call it as equality constraint. This is a inequality constraint. So like that we need to problem formation need to do. and to check whether these conditions are satisfied or not. And now I can see the optimization problem may contains only single objective problem, sometimes several objective problems. So if it is more than one, I can say it is a multi-objective problem also. That's why only one object I call it as a single objective function, and more than one call it as a multi-objective problem. An example of constraint single objective optimization is like this. What is the single objective optimization? Here, only one equation is there, our function y1 only. Like that, if you have y2, y3, and so on, all together we have to minimize at a time, that we go for as a multi-objective function. Like that, in generation, as I said, now cost and loss. So cost is one objective function, loss is another objective function, but both has to be minimized at the same time. Then you can say that multi-objective function. Cost and loss has to be minimized. In that case, we call it as a multi-objective function. And the range you can see for this problem, just is the only example how to represent that single objective function. These are the subjected to the constraints. Now, what are the constraints? These are the equality or inequality constraint. These are all the inequality constraint because it is not equal to 0. Suppose if any equation is showing is equal to 0, then it is a equality constraint. Whether it is a less than or equal to or greater than or equal to something, if I use or in between, these are all we call it as a inequality constraint. Now, terminologies you can see based on the problem, we can see iteration is a one terminology. That is once this many number of iterations we have to do to solve the problem, we can set that iteration. That is one of variable. You have to set that iteration count also. Then sometimes you call it as a solution. Solution is nothing but a population. The number of variables you can take control variable and what the values of that and all. Decision variable. Suppose final object or a goal, can say that marks. Suppose I want to find individual pass percentage of the student, then our decision variable is a marks, subject wise and position, grade, all these things you can consider. Like that, these are the some of the terminologies we can use. Objective function. The objective function is our what is your goal to find, that we can make use of as a objective function. I mean, there is a combination here, meta heuristic algorithms or something and optimization problem. Our aim is to optimize this problem or this equation using any meta-heuristic algorithm. In our case, there is a GA, genetic algorithm, PSO, and DE. These are the methods need to use to optimize the problem. So that's what we make use of that. And in this, what will happen? There is a function. Something initially will go for with random values because I don't know what is x1, x2, x3 value. Randomly pick up that. And suppose random values is 5, 2, 3. And substitute here, you will get function. What is function value? 5 square and minus 8 into 5 into 2 and plus x3 is 3, and we will get it as a function. Let us assume that function is minus 52. And what it will do, it will given to the algorithm, and again it will do the algorithm steps, and the new x1, x2, x3 value will come. Again you put it into function, the new function value will come, and this process is continuously repeat so that finally each case here is maybe minus 52. Later point of time something else value will come, something another value. Like that you have to do keep on this process until maximum number of iterations, so that you will get it as a final what you call it as a minimum value. So that is the way we can able to process this meta heuristic technique solutions. That's what I given here also. Conventional population based algorithm, randomly you have to generate, then we find some values, will submit, will get it as evaluation objective function. And after getting objective function, here you can see, suppose random value is 5 to 3. But if another subjected to constraints are there, in that subjected to constraint, what are they, x1 and then x2 and x3, all these things you can able to uh, put it into this. Suppose x1 range is given something 0 to 5 or 0 to 10, then it is suit. But x2 range is 0 to 5, then also suit. But x3 range is given, suppose 0 to 2, but you got the random value is 3, then you cannot use this set of values. So you can change, you make it to set it to minimum value. If it is violated in minimum or violated in maximum, you can set it to maximum value like that. And these are the how optimization problem and model function, as I shown you basic components of optimization problem. Objective function expressed in the main aim, that is only your main objective function, whether it is a minimization or a maximization. And set of unknowns variables are unknowns are also called as unknown variables, you can say that, which control the value of the objective function, obviously, because as a function, I shown you here something like this. This is a function. What is unknown parameters x1, x2, x3? Now, by controlling, by tuning x1, x2, x3, automatically function is going to change. That's what they mention here. Uh, Objective function, the set of constraints that allow unknowns to take a certain values, but excluding others. So, optimization problem is to find the value of the variables, whether it is minimization or a maximization function, while satisfying the constraint. Now, no objective function. So under the user does not particularly want to optimize anything, then we don't have any objective function. F of x will not be there. Simply whatever limits are there, you can make use of that x1, x2 values. That is only the thing. But if there is no objective function, there is no meaning of going for solution of the problem. And multiple objective function also there, with multi objectives are reformulated as a single objective problem. Sometimes what they will do is mm, suppose cost and loss is a objective function. There is a many approaches are there. Cost is one objective function, loss is another objective function, and you can give the weightage of different weightages. Suppose cost weightage is 0.8 or 80%, and 20% is loss minimization, and make together as a one function. Let it be f is equal to f1, 0.8 f1 plus 0.2 f1 f2. Second, the multi-objective, you can say this is one way. Individually, two functions you can write. Total f, I can write 80 percentage of weightage of f1 plus 0.2, 20 percentage weightage of f2. Like that, you can form one objective function and you can able to solve the like a single objective problem. We'll consider this is a multi-objective function, because here also we are there is f1 equation is there and f2 another equation is there. Here we'll get it as a cost equation, and here you can see loss equation. And at a time we are going to minimize this function that I considered as a multi-objective function. So like that, we can do many objectives. Suppose if I want to add another objective function, emission also want to minimize, then what you can do, you can change the weightages. This may be some 0.5 and this may be 0.2, total 7, no, remaining 0.3 you can consider as a F3 equation. Like that you can able to minimize. So this is the way of and problem, as I shown you in the previous. There is a minimization function subjected to the constraint. What is the first constraint? I call it as a inequality constraint. Second one I call it as a equality constraint. X is an n-dimensional vector called the design vector. F of x is called the objective function. And as I shown you, g of x is a inequality and I of x is a equality. Whenever it is equal to 0, then I can say it is a equality constraint. And there is a type of problem called constrained optimization problem and unconstrained optimization problem. That also we'll see in the next class. So we have constrained optimization. Another one is a unconstrained optimization. Now you can see the classification of optimization problem. There is a from here onwards one complete question. First topic as I mentioned, that slide also you can keep it here. Linear programming, because different classifications of optimization techniques or optimization methods or optimization problems or anything you can write like this. What is this? Linear programming. What is meaning of linear programming? The optimization problem consisting of two things. One is a function, another one is a constraint, subjected to constraint. Both objective function and subjected to constraint are in linear in nature. Then I can say it is a linear programming. So another one is a quadratic programming. What is quadratic programming? Objective function is a quadratic and the constraints are linear. So you can see the difference. Here both objective function constraints both are in linear, and here objective function is a quadratic and constraints are linear. And non-linear programming, both objective functions and constraints are non-linear. So here the problem we can classify linear programming, quadratic programming, non-linear programming, geometric programming also there. What is meaning of geometric programming? Objective and constraints are the synonymical. That means we can see that both must be in the synomials. So that we can see that there is a polynomial with the positive coefficients, means positive plus polynomial, then I can say it is a synomial. So there is a postmaster's word, we can represent that. And another one we can see there is a non-smooth optimization. So where either objective function or a constraints are not differentiable. So this the some method. Still, I will show you different classification. As I shown now, numerical methods, something I shown there, and then heuristic techniques. And another one is these are the some kind of classifications. And while in the classification based on the nature of the optimization, this you can put all things are in subheading fashion and write it like this as a total classification. That is one complete question, classification of optimization problems. And here the nature of optimization. What is nature of optimization? You can see in the iteration wise, we are getting as a different time, different values, something like this. In that, there is a local optima and a global optima. Meaning is, suppose, for example, in a classroom, 5 members are there. Let us assume that. In all 5 members, they are writing exam. They got some ranks. Now, which is the individual rank? We call it as a local minima for a particular person. In among 5, who is the least rank? He is the topper. That is a global minima. Suppose the rank 1 and like that rank 2, rank 3, rank 4, like that 5 people are there, 5 ranks are, let us do that. In that rank 1 is his local minima, first person, and rank 2 for this person is a local minima. Rank 3 also local minima for particular roll number, and rank 4 for him, this is a local minima. But what is the global minima? Among 5 members, who is having the lowest rank? that we call it as a global minimum. So let consider rank 1 is your global minimum. So compare to all 5 members, he is the topper. That means global minimum for first attempt. Like next attempt, again they wrote the exam, then their ranks will changed. Suppose the first person rank may be 3 and the second person rank may be 1, then third person rank may be second and this may be 5 and his rank may be 4. Like in this case, what you will check again, global minima is not changed one only. Suppose if it is marks may is that may be different. Global minima remains, but local minima, what happened earlier, local minima is 1, but again his local minima next time is 3. Now what we will do, you will compare these two, which is better. This one is a better, one is a better. That's why you will consider, you will discard the solution and you will keep on tracking the one only like that. So that solution will not take into account. That is the simplest way of explanation, local minima and global minima. Local minima means in the each iteration, the particular person value, or I can say that, that is a local minima. Global minima among all, who is having a least function value, that will be as a global minima. And the classification based on types of variable. So one classification is nature of optimization. Another classification based on the type of variable. There is a type of variables are binary and integer and discrete. So binary, as you know, 0 to 1, and then integer, then discrete variables. These are the different classification based on the type of variable. And deterministic or stochastic. Here, deterministic means then previous, you can see that in the previous slide also we discussed, and there is a uncertainties. You can see that bring about stochastic in nature, structure in the optimization. Finite variables are functions themselves. We can observe that variables are in finite if they are in the x1 and x2 and so on. What if variables are not finite? So then like that, there is a different kind of classification. We can observe another thing, considering the optimization problem. What is intern optimization? You just glance this image. There is a swimming pool here. One dog is there. Now there is a owner is throw one duck or plastic duck onto the swimming pool. Then what is the dog has to catch that. Firstly, it has to reach and then it has to catch. For that, it is the aim is not the shortest path. Your aim is to shortest time. That is the different you can notice when the what path should be the dog taken to touch the duck in the shortest time, not in the shortest path. But the straight line, whatever it is mentioned, this may be shortest path, but what we want is a very less time it has to catch. That is the objective. So like that, different problems, they may have as a different objective function. Now that means it is a optimization problem. How much time it will reach to get using algorithms, you have to find how much time it has taken to reach that shortest time to catch this duck, like that. So another classification, constrained optimization problem, which are subjected to one or more constraint. It may be unconstrained optimization problem in which no constraints exist. So again, I mentioned, no, this is another type of classification. Unconstrained optimization problem and classification based on the nature of the design variables. What is the nature of design variable? There are the two broad categories classification. One is the first category is the set of design parameters that makes the prescribed function. That parameters minimum or maximum. That may be the problem. Sometimes maybe minimization problem, sometimes maybe maximization problem, like that. For example, to find the minimum weight design of a strip, that there is a weights we have to the machine with two loads. I will show that these are the two loads P1 and P2, and our objective is to minimize the weights and such a way that where we have to place that P1 and P2. This is the total footing length is L, and the loads are P1 and P2. Distance between the loads, let us assume that constant, and required optimization to achieve by variable B and D. So you have to find the optimal value of B and D such a way that load weights must be minimum. Like that, while you're doing that calculation of B and D, it has to satisfy these constraints also. What is constraint? B must be greater than or equal to 0 and D must be greater than or equal to 0. So like that, we have the different problems and different constraints as well. And second category, set of design parameter which are all continuous functions of some other parameters. They minimize an objective function as a set of constraints. You can see if the cross-section dimension of the rectangular footing are allowed to vary the along with its length. You can see this diagram. Now, in that case also, we need to find the optimal value of B and D to meet this such constraint. So now your length is going to be varied 0 to L. Keep on varying and tune that, find the B value and D value to get our optimal value. So like that, we have different now classification based on the physical structure of the problem. Based on the physical structure, we classify the optimization problem, control and non-optimal control problem. And an optimal control problem, you can see mathematical programming problem involves in several stages. If we are going to do this control problem, that is optimal control, this involves several stages where each stage involves the there is a different kind of optimization algorithm. Sometimes there is optimal control prescribed manner you have to define. There is a two types of variables. One is a control or a design parameter. Another one is a state variables. Now we can look into that in trajectory manner also. Optimal control is one subject actually. Just here I'm telling is one classification only. The problem is to find the set the optimal or design variables such that total objective function has to be minimized. That's that overall stage is minimize the subject to set of constraints. And that we can see how we are going to be different again objective function, and you can make use of the equality constraint and inequality constraint. All these things we can make use. And the problem which are not optimal control problem is called as a non-optimal control, because two methods I told, one is OC optimal control, another one is a non-optimal control. The problem is not in the optimal problem, then we can say it is a non-optimal control. And non-optimal control problem, as I mentioned in the broadly classifications in linear programming, non-linear programming, like that. That a linear programming problem is what you call it as a option and subject to the constant variable in the linear in nature. Non-linear programming, if any one of the function among the objectives and constraint function is non-linear, then we can call it as a non-linear programming. So like that, we described several geometric programming. This is the way we can represent the geometric programming classification, quadratic programming problem. Like that, we can classify some classifications, and based on the permissible value of the decision variables. Under the classification problem, classified as integer and real values programming problem. And integer programming means what? If some or all the design variables are optimized problem are restricted to take only the integer. So then we call it as a integer programming problem. The real world, real valued programming problem. And here, which is the minimize or maximize problem. Anything is a objective function only. The real function by systematically choosing the values of a real variable from which an allowed set. When the allowed set contains only real values, it is called as a real values problems. And classification based on the deterministic nature of the variable, then some under this classification, there is a deterministic and stochastic problems also come into picture. We can see the what is the deterministic programming problem. All the design variables are deterministic. In this case, stochastic means there is a some or all parameters, that is a design variables, are probabilistic. That we call it as a stochastic problem. And for example, the lifespan of structure, which have probably input of the concrete strength and load capacity. Based on this only, we can able to find the life span of that structure. And like that, classification based on the number of objective function. This I already mentioned, no, single objective and multi-objective. Under the classification, there is a single objective and multi-objective problem also there. Only one variable is there, that we call it as a single, one function, that we call it as a single objective. Two functions means multi-objective function, or two or more. We can, as I mentioned, the more functions are there, we can go for as a weightage method, or fuzzification method, or genetic algorithm, what you call it as dominant. We can able to find this multi-objective functions also. So these are the some of the classifications of optimization problem. We'll see in the next class. If I have any doubt, you can ask me. Otherwise, you can leave.